There are likely more planets than stars in our galaxy. When astronomers first began discovering worlds beyond our solar system, the numbers grew faster than anyone expected. Thousands of planets were found in just a few decades, orbiting stars across the Milky Way. Many of them sit in what scientists call the habitable zone, the distance where temperatures could allow liquid water to exist. At first glance, the conclusion seems obvious. If planets are common and habitable zones are common, then Earth-like worlds must be common too. Life, perhaps, is everywhere. That idea became even stronger after the launch of the Kepler Space Telescope. By watching tiny dips in starlight as planets passed in front of their stars, Kepler revealed something remarkable. Planetary systems are not rare accidents. They appear to be a natural result of star formation itself. With hundreds of billions of stars in our galaxy alone, the implication was staggering. There could be billions of potentially habitable planets, but that conclusion depends on a simple assumption: that habitability is easy, that being in the right place is enough. As we began to study planetary systems in more detail, that assumption started to fall apart. Because the more we learn about how planets form, how stars behave, and how environments evolve over billions of years, the more it looks like Earth may not be the standard outcome. It may be the result of a very long chain of unlikely events. To understand why, we have to start by looking at how planetary systems are actually built. If Earth-like planets are common, then planetary systems like ours should be common too. For a long time, that seemed like a reasonable assumption. Our solar system was the only one we could study in detail, so it became the model we compared everything else to. Rocky planets close to the Sun, gas giants farther out, and a relatively clear inner region where stable orbits could exist. But as astronomers began mapping entire planetary systems around other stars, that picture started to change. Many of the systems we observe today look nothing like our own. Instead of a few widely spaced planets, astronomers often find multiple worlds packed tightly together, orbiting extremely close to their stars. Some systems contain chains of planets, all located within distances smaller than Mercury's orbit around the Sun. In many cases, these planets are locked in delicate gravitational patterns, moving in precise resonances that keep them stable despite their proximity. And in many of these systems, the inner region is dominated by a type of planet our solar system does not have at all: super-Earths. These worlds are larger than Earth, but smaller than Neptune, often several times Earth's mass, and they appear to be one of the most common types of planet in the galaxy. In many systems, they form easily and end up orbiting close to their stars. Our solar system has none. There is no massive rocky planet inside Earth's orbit. There is no chain of tightly packed worlds near the Sun. Instead, the inner solar system is relatively empty, with large gaps between the planets and no dominant super-Earth controlling the region. That absence may not be random. Planet formation models suggest that in many systems, material naturally builds up in the inner regions of the disk, allowing large rocky planets to form quickly. Without disruption, it would be normal to end up with one or more super-Earths close to the star. The fact that we do not have one suggests something interrupted that process. That interruption may have come from the giant planets. In many observed systems, gas giants migrate inward after they form, moving through the disk and reshaping everything in their path. As they travel, they scatter smaller bodies, disturb growing planets, and sometimes prevent entire regions from forming stable worlds at all. In our solar system, something similar may have happened, but with a very specific outcome. Jupiter likely formed early, beyond the snow line, and began drifting inward toward the Sun. But instead of remaining there, it reversed direction after Saturn formed and locked into resonance with it. Together, the two giants moved outward again, clearing material from the inner disk while preventing the formation of large super-Earths. This event, sometimes called the Grand Tack, may have shaped the entire architecture of our system. If Jupiter had stayed closer to the Sun, Earth might never have formed. If it had never moved inward at all, the inner system might have been filled with massive rocky planets. Instead, our solar system ended up with a rare structure, one where Earth occupies a relatively isolated orbit, free from nearby giant neighbors. And that unusual architecture may be the first filter in the chain. Even if a planetary system develops the right architecture, another filter appears immediately: size. A rocky planet must fall within a surprisingly narrow mass range to remain habitable for billions of years. Too small, and it loses the internal heat needed to stay active. Too large, and it may never remain a true terrestrial world at all. At first glance, this may not seem important. Earth, Venus, Mars, and Mercury are all rocky planets, yet they are very different in size. Why should the exact mass matter so much? Because planetary mass controls how long a world can remain alive on the inside. Smaller planets cool faster. Heat escapes through the surface. The interior becomes rigid, and geological activity slows down. When that happens, the processes that maintain an atmosphere and regulate climate begin to fail. Mars shows what this looks like. Geological evidence suggests that early Mars once had liquid water on its surface. Ancient river valleys, mineral deposits, and sedimentary formations all point to a past where the planet may have had lakes, perhaps even shallow seas. But Mars is only about half the diameter of Earth, and far less massive. That difference is critical. Because it is smaller, Mars lost its internal heat much more quickly. Its core cooled, its magnetic field faded, and its atmosphere gradually thinned under the constant pressure of the solar wind. Without a thick atmosphere, surface water could no longer remain stable. Mars did not fail because it was outside the habitable zone. It failed because it was too small to stay active long enough. Now consider the other side of the scale. Observations of exoplanets show that many rocky worlds grow larger than Earth. Once a planet becomes too massive, it may begin to hold on to thick envelopes of hydrogen and helium from the early protoplanetary disk. Instead of remaining a rocky world, it becomes something closer to a mini Neptune, with deep atmospheres and enormous surface pressures. These planets may orbit in the habitable zone, but their surfaces may not resemble anything like Earth. Beneath dense gas layers, liquid water oceans and exposed continents may never exist. There appears to be a transition region where planets stop behaving like Earth and start behaving like gas-rich worlds. Earth sits very close to that boundary, large enough to stay geologically active, but not so large that it kept a thick primordial atmosphere. That window may be narrow. Planet formation simulations show that small changes in the amount of material in the disk or the timing of when gas disappears can push growing planets across this boundary. A slightly more massive inner system might have produced a world 2 or 3 times Earth's mass at our orbit, a planet that could have evolved very differently. Many of the planets we find today fall into this intermediate category: larger than Earth, smaller than Neptune, with thick atmospheres we do not yet fully understand. Truly, Earth-mass rocky planets in stable, habitable zones may be less common than early estimates suggested, and even the right size is not enough, because long-term habitability does not depend only on mass. It depends on what is happening deep inside the planet. Even a planet with the right size is not guaranteed to remain habitable. What happens beneath the surface matters just as much as what happens above it. Inside Earth, heat from the planet's formation and radioactive decay keeps the interior active. Deep below the crust, the outer core, made mostly of molten iron and nickel, moves slowly as heat escapes from the center. Because Earth rotates, this moving metal generates a magnetic field through a process known as the dynamo effect. That magnetic field extends far into space, forming the magnetosphere, a protective barrier that deflects charged particles from the sun and high-energy radiation from deep space. Without that shield, an atmosphere can slowly disappear. We have seen this happen before. Mars once had a magnetic field early in its history. Ancient rocks still carry traces of that magnetism, but because the planet was smaller, its interior cooled faster. As the core lost heat, the dynamo shut down. Without a magnetic field, the solar wind began stripping away the upper atmosphere, molecule by molecule, over hundreds of millions of years. What remains today is thin, cold, and unable to support stable liquid water on the surface. Venus presents a different case. It is nearly the same size as Earth, yet it does not have a strong global magnetic field today. One explanation is its extremely slow rotation. A single day on Venus lasts longer than its year, and that slow spin may prevent the internal motion needed to sustain a long-term dynamo. Without a strong magnetic shield, the atmosphere evolved along a different path, eventually becoming the dense, heat-trapping envelope we see today. Earth appears to sit in a narrow intersection of conditions. It is massive enough to keep its interior hot for billions of years. It rotates fast enough to sustain a magnetic dynamo. Its core remains active, and its magnetosphere continues to protect the atmosphere. We do not yet know how common these conditions are on rocky planets. Magnetic fields depend on formation history, core composition, internal heat, and rotation rate. Small changes in any of these factors could mean the difference between a planet that stays stable for billions of years and one that loses its atmosphere long before complex life has time to appear. And even a magnetically protected world can still fail if its climate cannot regulate itself over long periods of time. That requires something even more unusual: plate tectonics. A planet can have the right size, the right internal structure, and even a protective magnetic field, and still become uninhabitable. Because habitability is not just about surviving, it is about staying stable for billions of years. On Earth, that stability depends on a process so familiar we rarely think about how unusual it may be. Plate tectonics, Earth's outer shell, is not a single unbroken crust. It is divided into large plates that move slowly over the mantle beneath them. Continents drift, ocean floors form and sink, and volcanoes release material from deep inside the planet. But the most important thing plate tectonics does is not shaping the surface. It regulates the climate. Carbon dioxide traps heat. If too much builds up in the atmosphere, a planet warms. If too little remains, the planet cools. On Earth, carbon does not simply accumulate forever, and it does not disappear permanently. It cycles. Rainwater absorbs carbon dioxide from the air and forms a weak acid. That acid reacts with rocks on the surface, locking carbon into minerals. Rivers carry those minerals to the ocean, where they settle into sediments. Over time, tectonic plates carry those sediments back into the planet's interior. Heat and pressure release the carbon again, and volcanoes return it to the atmosphere. This slow cycle acts like a thermostat. If Earth becomes warmer, weathering increases, removing carbon dioxide faster and cooling the planet. If Earth becomes colder, weathering slows, volcanic gases build up, and the planet warms again. The process is slow, but over millions of years it keeps the climate from drifting too far in either direction. Without this kind of regulation, a habitable planet may not stay habitable for long. Mars likely lost much of its internal activity early in its history. As volcanism declined and the atmosphere thinned, there was no strong mechanism to rebuild it. The planet cooled and remained frozen. Venus may represent the opposite outcome. Without a long-term carbon cycle, like Earth's, carbon dioxide released by volcanoes could accumulate in the atmosphere. With enough greenhouse gas, temperatures rise, oceans evaporate, and water vapor itself becomes another powerful greenhouse gas. Once that feedback begins, the climate can spiral into a runaway greenhouse state. Earth avoided both extremes, and one reason may be that plate tectonics never stopped. We do not yet know how common long-lived tectonic activity is on rocky planets. It depends on internal heat, crust thickness, the presence of water, and the mechanical strength of the surface. Too little heat, and the crust becomes rigid. Too much, and the surface may not break into moving plates at all. There may be a narrow range where tectonics can operate for billions of years, and if that range is small, then long-term climate stability may be rare even on planets that begin in the habitable zone. But even a planet with a stable climate and active geology can still fail, because climate is not controlled by geology alone. It is also shaped by the way a planet spins. Even a planet with the right size, a protective magnetic field, and active plate tectonics can still face another problem. Long-term stability does not depend only on what happens inside a planet. It also depends on how that planet moves through space. Earth is tilted about 23 degrees relative to its orbit around the Sun. That tilt gives us seasons, but more importantly, that tilt remains stable over long periods of time. It shifts slightly, but it does not swing wildly between extremes. That stability may not be automatic. Computer simulations suggest that without a large moon, Earth's axial tilt could vary chaotically over millions of years. Gravitational interactions with other planets, especially Jupiter, could cause the planet to wobble unpredictably, changing the angle at which sunlight reaches the surface. Large changes in tilt could produce extreme climates. Ice caps might grow and retreat dramatically. Some regions could spend long periods in darkness, while others receive intense sunlight for months at a time. Over long timescales, these shifts could make stable environments much harder to maintain. The key stabilizing force is the Moon. Earth's moon is unusually large compared to its planet. Most moons in the solar system are tiny relative to the worlds they orbit, but our moon is massive enough to exert a strong gravitational pull on Earth's rotation. That pull helps keep the planet's tilt from drifting too far. The moon itself likely formed in a violent collision early in Earth's history. A Mars-sized body struck the young Earth, ejecting enormous amounts of material into orbit. Over time, that debris came together to form the moon. But this outcome was not guaranteed. The impact had to occur at the right angle, with the right speed, and at the right time in the solar system's formation. Too direct, and Earth might have been destroyed. Too shallow, and the debris might not have formed a stable moon at all. From that violent event came long-term stability. The moon also drives tides, moving Earth's oceans and helping mix nutrients across the planet. Tidal forces may even have influenced the environments where early life developed, repeatedly exposing and flooding shallow regions along ancient shorelines. We do not yet know how often planets form with moons this large. Giant impacts were common in the early solar system, but not every collision produces a long-lived satellite. Many planets may form without one, or with moons too small to stabilize their rotation. Without that stability, climates may change too dramatically over time for complex life to develop. Again, the filter tightens. A planet must not only form in the right place, with the right size and the right internal structure, it may also need the right collision at the right moment to remain stable for billions of years. And even then, the planet is still at the mercy of something far more powerful: its star. Even if a planet forms with the right size, a stable rotation, active geology, and a protective magnetic field, its fate is still controlled by something far beyond the planet itself: its star. A habitable world needs more than the right distance from its sun. It needs a star that remains stable for billions of years, producing enough energy to support liquid water without subjecting the planet to constant radiation or violent changes in brightness. Not all stars can provide that. The most common stars in the galaxy are red dwarfs. They are smaller and cooler than the sun, and they burn their fuel very slowly, lasting far longer than larger stars. At first glance, this seems ideal. A planet orbiting a red dwarf could remain in the habitable zone for tens or even hundreds of billions of years. But red dwarfs have their own problems. Young red dwarf stars are extremely active. They produce powerful flares that release bursts of radiation far stronger than anything the sun generates today. Because their habitable zones are close to the star, planets in those regions are exposed to intense stellar winds and high-energy particles. Over time, that radiation can strip away atmospheres, especially on smaller planets without strong magnetic fields. Even if an atmosphere survives, constant flaring may make surface conditions unstable for long periods. There is also the problem of tidal locking. Planets close to red dwarfs often become locked with one side always facing the star. One hemisphere remains in permanent daylight, while the other stays in darkness. In some cases, a thick atmosphere could redistribute heat, but it is not clear how often stable climates can form under those conditions. Larger stars have different risks. Massive stars burn through their fuel quickly, living only millions of years instead of billions. That is not enough time for complex life to develop. Even stars, only slightly larger than the sun, may have shorter stable lifetimes, with brightness changes that can push planets out of the habitable zone. The sun sits in a narrow range between these extremes. It is large enough to be stable, but not so massive that it burns out quickly. Its energy output changes slowly over billions of years, giving life time to adapt. It produces flares, but not at levels that would constantly strip away Earth's atmosphere. Even the sun's composition may matter. Stars with very low metallicity may not form enough heavy elements to build rocky planets. Stars with very high metallicity may produce different planetary systems entirely. Earth formed around a star with just the right mix of elements to create both rocky worlds and giant planets. A habitable planet may need more than the right orbit. It may need the right kind of star, with the right lifetime, the right stability, and the right history. And even that is not the end of the filter, because stars do not exist in isolation. They orbit inside a galaxy filled with dangers. Even the right star may not be enough. Stars are not scattered randomly through space. They orbit inside galaxies, moving through environments that can change over billions of years. Some regions are violent and crowded, filled with radiation and exploding stars. Others are quieter, but may lack the materials needed to form rocky planets at all. Where a planetary system forms inside its galaxy may be just as important as how it forms. In the inner regions of the Milky Way, stars are packed much closer together. That density increases the chances of nearby supernova explosions, powerful bursts of radiation that can damage atmospheres or disrupt planetary climates. Over long timescales, repeated exposure to these events could make it difficult for complex life to survive. Closer to the center, The galaxy also contains higher levels of radiation from the supermassive black hole and from dense clusters of stars. These environments may be too hostile for stable, long-lived biospheres. Farther out in the galaxy, the problem changes. The outer regions of the Milky Way contain fewer heavy elements. These elements, carbon, oxygen, silicon, iron, are produced in earlier generations of stars and spread through space when those stars explode. Without enough of them, rocky planets may not form at all, or they may form too small to remain active for long periods. Between these extremes lies a region sometimes called the galactic habitable zone. It is far enough from the crowded center to avoid constant radiation, but close enough to contain the heavy elements needed to build terrestrial planets. It is also a region where stellar orbits are relatively stable, reducing the chance of close encounters with other stars that could disturb planetary systems. The Sun happens to orbit within this region. It is not too close to the galactic center and not too far out. Its orbit around the Milky Way is nearly circular, keeping the solar system away from the most dangerous parts of the galaxy for billions of years. Even this may not be enough. Stars move through spiral arms, pass near star-forming regions, and experience changes in their surroundings over time. A slightly different path through the galaxy could expose a planet to more radiation, more gravitational disturbances, or fewer heavy elements during formation. By the time we reach this scale, the number of conditions that must be satisfied has become very small. A planet must form in the right system, around the right star, in the right region of the galaxy, and remain stable for billions of years. And when all of those filters are combined, the result begins to look less like a common outcome and more like a narrowing funnel. At the beginning, the universe looks full of possibilities. There are hundreds of billions of stars in our galaxy, and around many of those stars are planets. Some of those planets orbit in regions where liquid water could exist. With numbers like these, it is easy to imagine that Earth is just one of countless habitable worlds, but each time we look closer, another condition appears. A planetary system must form with the right structure. A rocky planet must fall within a narrow range of mass. Its interior must remain active long enough to generate a magnetic field. Its surface must regulate its climate for billions of years. Its rotation must stay stable. Its star must remain calm and long-lived. Its orbit must lie in a safe region of the galaxy. Each of these requirements alone may not seem impossible, but together they form a chain of events that may be very difficult to repeat. This idea is sometimes called the rare Earth hypothesis. It does not claim that life is impossible elsewhere. Simple life may form on many worlds, but complex, long-lived, Earth-like environments may require so many conditions to line up that they become uncommon, even in a galaxy filled with planets. This possibility also connects to one of the oldest questions in astronomy. If the universe is so large, where is everyone? The Fermi paradox asks why, in a galaxy with so many stars and so much time, we have not seen clear evidence of other advanced civilizations. There may be many answers to that question, but one possibility is that worlds like Earth are not easy to make, not because planets are rare, but because stable, long-lived environments may be the exception rather than the rule. Earth may not be special because it exists. It may be special because it survived. Out of all the planets that formed, out of all the systems that evolved, this one passed through every filter without falling apart. And that does not make the universe empty. It makes it fragile. Because if worlds like ours are rare, then the only place we know where life has survived for billions of years is the one we are standing on. Join us next time as we explore more mysteries of the universe.